Hello, all developers. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device. This is discussion 103 for all IBM Qiskit machine learning tutorial seminar. I'll be going over all 12 of these modifications. I was able to improve most of these. So the big thing with Qiskit machine learning is it's just like if you're doing machine learning or deep learning right now, you're using Python notebooks, and it's a very familiar setup. So Qiskit provides fundamental quantum computational building blocks for the rapid prototyping of models without having a deep understanding. So you can see pretty clearly if you've taken some tutorials, what are the trainable parameters that make this quantum, this version of machine learning. And some of the tasks are common: classification, regression. There's a GANs I put in there as well of these 12. And then you also have, changing the architecture of the algorithms is important. And even if the models are small with the training sets, it's important to understand that even if you get some of these gains, they can translate into bigger problems to be solved. And I put this in the format of purpose, plan, and action. So the purpose being the reason modifications need to be made, the plan, going down this funnel, the general approach, what that could be changed, and the action is the actual steps that I took, and the corresponding responses as well. So if you have any questions at any time, feel free to raise a hand. And this tutorial is actually the first one that they put up. Now, I would recommend, if you want to do machine learning with Qiskit, to go over this. So it's got estimator, QNN, and all the different. So this is basically the framework that Qiskit uses for machine learning. So what I chose to do on this particular one is modify the circuit. So on the left, you'll see the H, RY, RX being the weight. So what makes this quantum machine learning or quantum-inspired machine learning is that over the course of the run, so you have batches just like in machine learning and epochs and those types of things, is the rotation angles get optimized to a certain amount to increase accuracy, decrease loss, or other things that you would want. So it's weights and biases, but done with quantum, with qubits. Now, the way that this one was drawn here is you have your Hadamard gate, the RY, and the RX, and it outputs a specific, and then this model is weight gradients. So the modifications that I made for in this case is that I added an additional RX gate. So, this is represented by the fourth line of the code, and you can see that the weight gradients are going to be different. Now, the whole thing with quantum machine learning, quantum-inspired machine learning is, qubits have more information, complex numbers than bits. So it's not thought that we need as many trainable, quantum bits compared to classical, but at that same time, we need more of them. That's the general notion of it, either through more RAM through simulators or better understanding of how exactly, qubits interact with the larger data sets in specific. And so there's been papers on that as well. So you'll find this is basically an intro to all these other tutorials. And like I said, for those that are just entering, definitely check this out, the first one that you do, because it has a lot of the terminology that's used in a lot of these other demos as well. Okay, so going over number 2 here. So this is neural network classifier and regressor. So as you can see here, so starting on the left with the tutorial circuit, ZZ feature map is hard to represent as a bigger ZZ feature map. So I just put 2 of them together. Now, when you're researching this and understanding how to develop machine learning models in Qiskit, you have to go through documentation. So what I mean by this is, for this embedding layer, for this ZZ feature map, you would type ZZ feature map into Qiskit or Google, and then it'll come up with this nice page. Now, the 2 in this case represents the number of qubits. So it's you have Q naught and Q1. And if you look at the documentation, it defaults to 2 repetitions. So that's why I set this one to ZZ. In some cases, you can get it to expand or show the actual gates. But the key in these is to really understand these single pages that say have real amplitudes, Z feature map, because this is where you can make a lot of the changes that can help affect performance in your models. Okay, so you'll see on the left here, and this is basically the, sometimes they're loss curves or basically a measurement of performance. So it goes down over time, which is good for the iterations. And in this case, this small 20 sample set, it got 4 of them wrong. And that corresponds to a classifier score of 8.8 or 80%, denoted by these red circles. Okay. So what I did for this particular one is that the modified circuit, so I mentioned before, the default number of repetitions for ZZ feature map is 2, but that's not the 2 that's on the screen. It's built into it. It's just how that specific feature map is. So I went in and I changed it to repetitions equals to 1. So it's going to be smaller feature map. And you can see the loss curve was more favorable. So you get this flat line to 0 earlier than the previous one. And then in the classification one, it had different ones that it didn't classify correctly. But overall, it was a higher classifier score with only 3 instead of 4 of the other ones. So even though a lot of these examples are small or toy, if you can get a really good understanding of the feature maps, the ansatz, and so forth, then you have an advantage as we have access to more qubits with simulators and better understanding with data sets as well. So feel free to raise your hand if you have any questions regarding any of these. This is number 2 that I'm going over right now. And we saw.
I have
yeah, go ahead.
Sorry for the interruption. I have a question in the previous slide as well. So in the previous slide, you made a change, like you added one more RX gate with a weight parameter. So my understanding is like if we are applying 2 RX gate consecutively, it's just like you're adding 2 parameters, that's it. So how does that make any change in the circuit?
It makes a big change. So, just like if you were to switch from a deep learning neural nets are up to billions, if not trillions of parameters. So every single one counts as far as it changes the weight gradient.
I mean, my question is that like you're applying RX and then you're applying RX again. So the first one, let's say it's θ1 and the second one is θ2.
Right.
And both are trainable parameters. But if I just apply RX with θ1 plus θ2, it's the same thing if you're applying 2 RX.
That's not my understanding, but we can come back to it. So I'll get through the slides. If you have questions for the specific slide, and then we can come back to these for sure.
In this slide, I was just going to ask, like, so you're showing like with less number of input layers, you can have better performance?
Yeah, sometimes it's more. It just depends on the model. It depends on the data set. And that's where what would make sense moving forward with a lot of this is to develop spreadsheets that say like, it just goes through these models automatically and changing layers. And usually qubits is trickier because qubits is like the number of features. They're classes.
Yeah, but my point here is like, there are some papers that show advantage of using data re-uploading. So how do you compare that thing with the data re-uploading thing?
I'm sorry, I missed, you said compared to what?
Compared to data re-uploading techniques.
Real encoding?
Data re-uploading. You have your input layer, then trainable, and then
this is a huge field. So I'm not going to cover data re-uploading in specific for these 12 because that's not part of it. But we'll stick to if we have questions for the particular slides, then we can come back towards the end.
All right, no problem. Thank you so much.
Yeah, so this next one, so training a quantum model on a real data set. So for this particular one, what was changed is the number of repetitions. So in this case, so you don't want to think of like repetitions like it's just no thing, because the efficient SU2 has a certain block of number of gates per repetition. So when you increase it from 3 to 4, it's not just one gate, it's a block of gates, sometimes 9 or 10 or even more. It just depends on that specific circuit. And so for this one, it was challenging to get better scores for it. And in a lot of these models, they have different sections. So this section, is the efficient SU2 with 2 dimensions in specific. So I was able to get a test score of 0.79, a little bit better than the 0.78 that the model has got. And another thing I experienced with a lot of these is when I run the Qiskit, a lot of times the run times were a lot slower than the Qiskits. If I look at my specific models and what it says my specs were, sometimes that's like 8-core, you know. So it's possible also to do GPUs, but also keep in mind when you're running these models, always don't regard the first run. The first run has initialization between different, you know, different parts of the model that you're running. So a lot of times you run first and then you run again and then you're second. And if you make minor modifications from that or rerun that model, those are more accurate as far as time. But, you know, performance or accuracy or loss are pretty common. So any questions regarding this specific model, this number 3? And then here's the 4th one. So on this one, what shined out the best is basically this clustering score. So the modified circuit, and I wasn't able to show because drawing circuits can be challenging, you know, because if it's based on the notebook in that specific way it's written. So the one on the left is this ZZ feature map, which is an embedding layer, which takes classical data into quantum states. And the entanglement in it is linear. So linear entanglement, you know, is not as complex as full. So what I did on this specific one is I changed entanglement equal to 4. And in this specific case, you can see what's going on with ZZ feature map. Now, if you open up the documentation, so if you Google search or within Qiskit, this first part is actually numbers of qubits, but it's written as feature dimension equals ad hoc dimension. So earlier in the notebook, feature dimension is equal to 2, okay? So it's taking that 2 from feature dimension and putting it in the space of number of qubits represented by 2 qubits here. Now, that helped out a lot for this specific case. So sometimes it helps to do more entanglement, sometimes it doesn't. And this is where it gets into like, and especially where the industry's going is we need to have an even greater understanding of like changing entanglement. What does that do for this specific data set? So I was able to increase the classifier score from this 0.73 to 1.0 just by changing that entanglement on that specific case. So any questions regarding this model? This is number 4. And then, so here's number 5. Yeah, go ahead, Ron.
Kevin, what was the underlying ML model here?
So quantum kernel machine learning on this specific one. You know, this one I think had 3 sections for it. I would have to reference it to it. And actually, these links at the bottom, so this 4 link is the actual model. And then so the 4A, these are all up on GitHub. So if you look at, so it's Kevin Kwachak, no spaces, or medical quantum machine learning, that specific one. So I would have to go back for that for the overall machine learning model.
Right. So the kernel technique is something you can apply to like a support vector machine or maybe even a principal components analysis machine.
Yeah.
Which it looks like you use something around a clustering model. I'm not familiar with that one though. But all right, thanks. I'll check.
Yeah. So again, a lot of these, they do take a fair amount of research as far as like this section to this section to this section. And you know, it's just, you know, it's hard to improve everything at the same time. But even if you see small benefits in here, they can relate to bigger, you know, if you have bigger problem sets, more data, that type of stuff as well. And then, so here's GANs. So GANs is generative adversarial networks. And you have 2 of these networks and they're going against each other. And it's well known that you could do this with quantum. So in this specific case, I tried and tried and tried. And the thing that was most productive was reducing shots by an order of magnitude from 10,000 to 1,000. It didn't seem to affect, so the end result are these difference between CDFs here and then the right one here. So overall, 10,000 shots, still probably better as far as not going as high in red and as low as blue. But it wasn't that much difference. So for those that don't know, so shots are typically take longer, use more compute resources, for even, simulators, or if this could run on real hardware. And then this next one, I did a big presentation on this. This is IBM's or Qiskit's torch connector. So torch connector is basically inserting your quantum algorithm efficiently in the middle of a bunch of torch.nn code. So if you have, all of these layers that you would find in, say, like a Hugging Face advanced models, and the hard part is getting that performance boost, using quantum that's not just, similar, if not just a little bit better. And I'll get to that as far as where the industry is going with these circuits, with quantum circuits. So learning rates, in theory, if you make it a lot lower, and I'm looking at optimizer Atom here, it's a very popular optimizer. So same thing here. So if you want to, and you're going to have to, if you do machine learning and quantum, you type in Qiskit or you type in Google, and this would be Atom and then Qiskit. That'd probably be the quickest thing. Now that's going to open up a sheet, and it's going to tell you everything that you can change for the Atom optimizer in Qiskit. So they have their learning rate set to 0.001, and I actually increased it, which would be less steps. And in this case, it actually helped a lot as far as the test loss. So you can see here, the loss goes down, as things progress, test loss over here, -1.78, test loss over here, -7.04. Overall accuracy from 98% to 100%. Now, this is 150 images. So it's 100 training and it's 50 testing. And because this went well, I took this further and I 10 times the amount of data. Now, MNIST data set is 10 digits. It's 0 through 9. And this is just looking at 2 classes. So, it's, if you look at like the best ever MNIST, that's likely all 10 digits. It's not binary. But nevertheless, I ran it for 1,000 training and then 500 test with this learning rate that worked good before. And I get 99.5% accuracy, a very low loss as well. It's 150 images, 150 binary classes. Well, this is a simple data set. Like zeros and ones, they're pretty distinguishable by a computer. But you get more complex and you want to find out if your settings are right. So anyway, this is a good temp. This is up on GitHub, and you'll see large or just regular for that. Any questions at this point? And then the Pegasus QS quantum support vector classifier. This one is supposed to be faster than other QSVCs. So that's the reason of this demo. So the circuit was not changed. However, the tau, which is a step function, I reduced it by half. So for a data set like this with 20 points, do you really need that 100 tau steps? That was the hypothesis. And in this case, it was the same exact landscape. Now, these dots, the blue dots, represent the train. So it'll tell you here, train and test for the B class. And then the A class is train and test for the A class. Those are the dots, okay? So you want the dots to be in the respective colors. So you can see for the red ones, all of these red test and train are in the red island. Now, what changes based on your modifications are these blobs, okay? So sometimes they look like islands or like peninsulas. And as you change the notebook, that's what it's trying to encapsulate more of the dots. So for, 20 dots, this is a small data set. In this case, 11.5% speed up and getting this pretty much the same exact map in this case to try to get these dots in their respective colors. So, you have to look at these. So this model does not take much to run because there's not much data, right? So 20 pieces of data, I believe it's 10 and 10 for red and blue. It's not that hard, but like I said, like it's a step, right? Because if you make other modifications to the notebook and you're up to like 30%, then can you get 30% on more data? Those types of things. So, and again, this is a binary classification for 2 classes in this specific case. Awesome. Okay, so this one, so quantum kernel training for ML applications, same exact circuit. However, this is another learning rate one. So where I would start with a lot of these models is the circuit. If you figured out, more efficient circuits, and I'll show you another good example coming up here. Definitely check the learning rates, and learning rates typically it depends on who made the model. But like if you check some of the values below and you check or say if it's 0.05, so a good thing to check initially might be 0.055 or 0.045. So in this case, 0.048 helped the most. And this was a pretty well optimized model because, using this different learning rate, we both got 100%. However, in this case, it's the loss curve, typically you want a smoother curve that goes down in lower loss. So you can see the one on the right, smoother curve that goes lower down in loss. And in this specific case, it's likely going to run a little bit slower because the learning rate is been decreased. So that's more steps of, anything, machine learning, quantum machine learning. That's typically the case. Is it's going to run a little bit slower, but there's limits of how low you can go, and there's every optimizer is pretty much different as far as the types of curves that you can get. Okay, so this next one, saving loading Qiskit ML models and continuous training. So the circuit was kept the same. However, I found this really good optimizer. So it's this AQGD. Now, AQGD stands for Analytic Quantum Gradient Descent with Epochs Optimizer. Now, other platforms have quantum-specific optimizers, and I believe they're only available through, say, Qiskit and other libraries too. They might do a different one. But as you can see here, using COBOLA, which stands for Constraint Optimization by Linear Approximation Optimizer, this is how they call it objective function values goes down. So you can see with this, orange and then the purple, and then goes down like that. Now using this AQGD, it's a different one. So I would be very interested in developing this more, also moving to bigger data sets, because the loss curve or objective function value, which you want to go down with more iterations, is, that looks like something that you would want to develop more with on the specific one. But nevertheless, a lot of IBM's optimizers use COBOLA. COBOLA is the optimizer. Now, in this specific case, so you see 5 of these with red circles as the train score, or actually, hollow and solid stand for different things. But nevertheless, train score 0.9, test score 0.8, and in this case, a little bit better on the train score, so 0.933, and then the same thing for the test score. So the test score are the hollow dots, and then the train scores are the solid dots in that specific case. So, about 3.3% better train score. But with these data sets that are so small, if you have 50, this might be 50, something like that, it's not saying a ton, right? But it's a step towards understanding modifying models and how that changes things, basically. Okay. Any questions at this point? And we'll have time for going back to specific models. So
I have a just quick question here.
Yeah.
Not like maybe very relevant to the slide, but I just wanted to ask, like, if we have PyTorch layer and Qiskit layer, do we have any way to have a different optimizer for quantum layer and let's say AQGD for Qiskit layer and Atom optimizer for PyTorch layer, like the classical neural network layer?
In that case, I don't think so, because I've done this other demo that is not part of. Well, actually, when it gets into, PyTorch, it's basically the quantum part's been figured out, and the output is what's is essentially binary. So it's treated like a special Python function. If you're, replacing a fully connected layer in that specific case. Now, other ones have said, like, I believe that you can use a loss function that's of NumPy and say, like, a PyTorch optimizer. Those types of things I think are possible.
Okay.
But within the actual layers, I think that's going to fall under, that's no longer considered quantum. Like, it's been calculated, and those specific layers, it is binary, and then you're going to have you're going to be processing that just like machine learning. It's just, Qiskit or other libraries have taken care of the quantum calculation part with a quantum circuit. So I think a lot of this is getting better. And say, for instance, like on a different library, you can do NumPy with, 6 quantum specific optimizers. And then there's other NumPy ones. And by the way, there's a NumPy optimizer that allows you to change how the quantum circuit architecture is, say, remove layers over the course of epochs. You can do that. But it's going to take some technical expertise for sure. I say, if you want to use this specific optimizer over here and here, a lot of times they'll tell you on discussion forums it's possible. But typically the rule of thumb, at least in this stage, is, if you're in NumPy optimizers, try to stay in NumPy. Now, if you're running PyTorch models, that's where it takes additional expertise. I don't think that's something that's just because when you go to train your model and it says, like, it's taking this part, and this part, well, all of those are typically PyTorch or NumPy.
Okay.
So yeah, it's a type of thing definitely in the forums, in these libraries, to ask specific questions, because it seems tricky to me, because if you're training a model all in PyTorch, then how is this NumPy optimizer loss function thing? So, like I said, from what I'm hearing, it's possible, and it'll likely get better. But at this point, PyTorch doesn't, I don't believe, have any quantum specific optimizers like NumPy does, right? And Qiskit, is typically using, this Torch framework. So yeah, I think it's something that it'll get better in the future.
All right. Thank you so much.
Yeah. Any other questions? And then, so effective dimension. So I had previously optimized this very well to the point of changing individual numbers of samples and these things, but it wasn't very comparative to the say the Qiskit original demo. So what helped the most in this specific one is upping the feature map. So a Z feature map is smaller than a ZZ. So Z, I don't believe, uses any entanglement in quantum, and ZZ does. And that's basically all that it took. Now, what these ABCs at the bottom mean is basically we want to have a good understanding of, so they call it global and local effective dimension. And it's essentially a capacity measure that you would have in machine learning, but this is what we're doing in quantum. Now, this sounds all fine and dandy, but IBM researchers have found that you can increase, overfitting with higher effective dimensions. So you'll see here on the left, so this blue single curve is a global effective dimension, and this, the axis is a little bit about 0.86. And then this right one is for trained weights and for untrained weights of local. Now, it's believed that local effective dimensions is going to have a greater impact than global. And that's where the research, is likely going to be focused. So when this was changed from the feature map or the embedding layer, or where the classical data goes to quantum, the global was increased to, and you can see the axis is now from 0.93 instead of 0.86. And then for local, it increased significantly. So you see it's 0.75 for the previous. max, and this is 0.95. So you can get higher with these, but a lot of times you're trying to get 100% on different types of graphs and still trying to, get the maximum effective dimension, right? So a lot of these, concepts and Qiskit and other researchers too, is you'll go through this thing and then, find out, well, if we do this, it tends to, maybe correlate to overfitting, which is not desired in machine learning for this specific one. Okay, so this one was my very first as far as, demos ever done. So you'll see on the left, so this is basically, if you're familiar with convolutional neural networks, it's a staple. Any, medical developers all over the world, ResNets, AlexNets, or convolutional neural networks. Now, in this specific case, the tutorial survey, this is a part of the convolutional layer. And this is the exact circuit. So what was changed is it was just doubled, right? So a lot of times, if you have certain values that are odd, go up or down in odd. If you have certain values that are even, go up or down or even. This is a rule of thumb that works pretty well for optimization, other things too. Now, with circuits, what I found is a lot of times doubling a circuit helps, of that specific type. And then, usually if you get much greater than that, then that's not the case. But there's a lot of examples that I found doubling, this convolutional layer effectively got 100% in train and test on an 8-pixel image compared to 94 and 73%. And this one I had to increase the maximum iterations, or the time it goes through, from 200 to 275. So on the left is basically the tutorial with increased iterations. On the right are those same iterations, but with a modified circuit. So, you want to think, so in this specific case, for this is earlier in the code. So this convolutional layer is incorporated eventually into 8 qubits. And those 8 qubits effectively, for 8 pixels in this case. So using this model, if you had like a 28 by 28 MNIST, image, that would take like over 700 qubits for this specific case. So that's harder to do with quantum-inspired machine learning, where we're typically, 30 qubits, 40 qubits. So this has a lot of quantum in it, right? So convolutional layer, pooling layers, they're all circuits, all quantum circuits. So it's very interesting because it's, even though the data set's small, if you want to do image classification, this would be a good place to start. And, especially as we get more access to more and more qubits. Okay, so this is 12. So this is the quantum autoencoder. Now, I was able to show the modified circuit in this. Now, the thing that pops up over and over again in Qiskit is your embedding layers, which are like Z or ZZ feature maps, and then your ansatz. Now, your ansatz are typically trainable, which means that, for what was modified here, this is what makes it QML. So instead of 5 repetitions, and you can count, and you can see, in real amplitudes here, there's no other commas, but there's stuff built into this. So there's 1, 2, 3, 4, 5, and this looks like linear, and I think linear for real amplitudes is the default, and that's why you're seeing this pattern for the C0 gates, is because without changing it, this is how it shoots out, right? So you have to study the documentation in order to understand the circuit or change the circuit to what you want. So in this case here, you see the 3 repetitions, 1, 2, 3, and of course, it's going to run faster. So in this specific case, about 10–11% faster because of less layers in this specific one. And it depends on data sets and all that kind of stuff too. So you see the fit 36 to 32 seconds approximately. And this output state from 0.9939 to 0.9997, right? So the takeaway message with a lot of this is, even though these are small, if not toy problems, is that, if it's working well in this, try it, keep running it. on different data sets and scale it up. And this code is basically Apache 2. So again, the 12 is every one that says just the number, that's the Qiskit. And then the 12A is the modified code. Now, what's important to see in these cases is that I went over this, with embedding layers and trainable ansatz. And, you need to basically, if you want to do this the rest of your life, develop a system where it's just like, okay, well, this, every odd repetition, I'll try it up and down, and then optimizers. Well, I don't like Atom or I don't like Kobola. I want to use this quantum specific one, which needs more research because, Atom in specific or Ada grade or those types, those are well established in deep learning. So what quantum has to do is catch up, right? So we don't have years and years of, inventing the perceptron, and which is inside the neural network in classical. And now we have this PQC algorithm, and I'll get to this. But basically, where we are limited in parameters, right? So if you have more data, if you have a bigger circuit, more qubits, you're not going to get anywhere close to how we are today to millions or billions of parameters or trillions, I think with OpenAI and large language models. However, with the quantum bits having more information, we wouldn't necessarily need to get to that level, but I think a lot of us would say we're maybe thousands. I don't know if anybody's like 10,000 parameters, these rotational quantum gates. And, especially with new optimizers that are specific for quantum, those deserve additional research as well. So the purpose, plan, and action for quantum machine learning is to improve all these metrics, with runtimes and the number of trainable parameters, these types of things. Quantum simulators are going to have to improve too. So even though we have like a QSIM simulator by Circ, and we have NVIDIA's multi-GPU, multi-node that's going up to over 1,000 qubits, it needs to go more mainstream. And I believe I'm just not getting enough as far as the standard traditional, we call it parameterized quantum circuit model, which was used in all of these demos and other libraries too. That's, it's just nobody's reporting, even if you heavily optimize things and say, this was done exactly to classical, we need a new PQC model. It was meant for quantum hardware, noisy quantum hardware in 2012. And, basically greater accessibility to CPUs and GPUs. There's CPUs and GPUs that people have a hard time multi-threading, meaning take advantage of multi-cores and CPUs. GPUs, you have to typically pay a little bit. And all this advanced deep learning, coming from, years and years and years of researching and, setting up neural networks, and, this is the best way to do parameters, that's going to have to slowly trickle into these libraries. So Qiskit and others as well. So this is the GitHub. So like I said, there's a GitHub for each of the Qiskit tutorials. And I think a lot of these are a good place to start. I mean, it's not a ton. And then, so let's open this up for questions. So first, we're going to go back if you have specific questions about specific models or tutorials. So there's 12 of them.
Can you please go back to slide number 13? So
Okay.
here you were mentioning about like even or odd, something like that. I think I missed that part. So can you repeat that part again?
Yeah, well, first off, and I've done other Qiskit studies just trying to get the best results and best probabilities and these types of things. Doubling the circuit is the first thing to do with any quantum circuit. And there's also studies, symmetry. You'll see a lot of circuits and papers that use symmetry. So say, for instance, like the symmetry with this would be if you took that second chunk over here and then just flipped it over the x-axis. So it perfectly reflects itself. That would be symmetry. There's also studies that, they try alternating, and this is more for just a specific smaller circuit, but you could also alternate between embedding and training layers, or embedding and training gates, just specifically gates. And I've had some success with that, but if you've heard it in previous discussions, something as easy as for embedding, just trying HRY, because the output of that is it's the surface area of a sphere. So that tends to, it looks like, put the data on the outside of the sphere. And then the next step is basically say, I want 10 classes or 100 classes predictably on the outside side of the qubit to separate the data. So those would be the next steps. Now, the other stuff is basically, these just work for me. So if you have a specific, learning rate that's like odd, then just increase it by an odd number. So if it's like 0.05 to 0.07 or 0.05 to 0.03, and those seem to work because, with models and all this type of stuff, a lot of time, and with circuits too, figure if you have a entangling, if you have a C0 gate, so that's 2, right? So the next step with this circuit, if you wanted to go from 2 to 4 qubits, wouldn't be 3, right? Because you would want the entangling, because entangling gates take up 2 wires, so for something simple like that. Yeah, so, there's a lot of there's a lot of efficient ways to do things, and that's some of them that I found.
Okay, thank you.
Anybody else?
So for this number 11, your Q0 and your Q1 inputs, how many pixels does that represent?
So a lot of these get built up to bigger circuits. So this is the original one. You start off, say, like, this is like, it's not like transpiling, but like, if you're starting with 2 qubits here, and then it gets built up with, the pooling layer to the right of the circuit. And then this essentially, if you look in the upper left-hand corner, those are the 8 qubits. So this would be, in the blue one, convolutional pooling, convolutional pooling, convolutional pooling. But the way that the demo is made is, it's easier to start off with something, smaller qubits and work it up. Right, I think that's
so the circuit that's shown is just one set of qubits from that block of 8.
Right, it's into that block of 8, and then if you look at the demo in specific, then it's the very first circuit that you can modify. So you can, I didn't put the whole code, I just put for the optimizer here, but in the demo you could get it from it's up on GitHub.
Okay.
Yeah, and you'll learn so much more that you weren't intending with a lot of these demos. Awesome. So there were some in the chat here. So what about initial onsets? Did you find initial that maybe reduce the computation? So, I mean, typically the more gates and the more entangling is the higher compute resources are needed. Typically with a lot of these, like with qubits, almost always goes up exponentially the amount of RAM needed and the amount of time needed, increasing additional qubits. So some of these, might be constructed to, not use as much qubits or resources up front. And they do take some study. And feel free, are there any questions about the slides?
I will just go with the first question that I had, like RX and then RX again, like the 2 weights. So can you just repeat it again? Can you explain it? Because to my understanding is if we are applying 2 RX gates and we are training both parameters, so it does not make any sense to me training 2 parameters when you can have just 1 RX and just add them weight 1 and weight 2.
This isn't, so an XX would cancel. So if you bit flip, so if you do 180 degrees, 180 degrees, but the theta values on these can be different.
I mean, I understand these are theta values, not just the X poly X gate. My point here is you are training weight 1 and you're training weight number 2 as well. So you just need to add both of them. and you just go with one RX gate there.
I mean, I could see it for X, but I think there's cases where if you can have more any R, Y, X, Z, I think it would make sense to have more of them because each of those can adopt a different angle, right? And that's
I
it's
mean, if they
similar.
have like one more gate in between them, then it makes sense. Like if it's RX, RY, and then RX, then maybe different parameters that you can learn. But if
Yeah,
it's like just RX and then another RX, so it's like you first rotate your qubit to this way and then another angle like this. That's it.
I
That's
mean,
my intuition for applying two RX consecutively.
yeah. I mean, my take
If
with this is
is
basically from classical. So you have all of these different, trainable parameters, and the values of the two RXs can be different. But if you're saying if it's weight 1 and weight 2, that would be different. So
well, there's
Even if it's the same weight.
this goes back to my question. If you look on the upper left corner, you see the complete circuit. Which appears to be four qubits. Is that right? So
yes,
this graphic is a little misleading because it's just showing you the timeline of one of those qubits. Those qubits obviously have to be interconnected. So I'm thinking these graphics are just not showing the cross qubit like C naughts
yeah.
or two
And
qubit.
a lot of these demos, there's a lot to them. So the approach with all of this is find something to improve. So say if it's something earlier, it typically, would carry on through the rest of the, your final, classifications or losses, those types of things. If it's something at the end, it's probably easier to modify because that if you change an onside or, embedding layer at that point, only the things after that code are modified. I see what you're saying, like, if it was RX weight 2, weight 1, weight 2, but if they're both getting the same weight. But what's interesting is that the weight gradient's calculated differently. So,
Okay, but to his point, if that upper right Q circuit was a standalone single qubit circuit, the compiler transpilers are going to compress those RX into a single operation. But
Okay.
but again, I think what we're missing here is this graphic isn't really showing the total circuit, which is kind of hinted at in that upper left corner graphic, the little icon up there.
I think he's just showing like single qubit QNNs, I guess, like Kevin. Is it right?
yeah, I mean, I don't,
Yeah,
if
but
the weights
how do
were
you do
different,
a QNN with a single qubit?
yeah, if the weights were different, I don't think they'd be transpiled the same, right? RX weight 1, RX weight 2.
I mean, you can see in the code it addresses more than one qubit.
No, actually,
Doesn't it?
so
Okay.
yeah,
Or does it?
H0, everything that ends in 0 is the 0th qubit. And then so the params, params
Oh, there's the
1, 0.
parameter IDs
Yeah.
here.
Yeah. So you can see it from the Hadamard H0. So, sometimes it's tricky, with
So
Qiskit.
is this like the first step in the tutorial?
So yeah,
Is
this
that
is
what
the
this one
first
is? Yeah.
tutorial.
Yeah. But is it like the first step in the tutorial? Like they show you?
I think they put it there.
Yeah.
Basically, it's a good start because it talks about estimator QNN and sampler QNN, and basically the function. There was no accuracy or losses in this specific one. It's just saying that
Yeah.
if you change specific gates, you can change the gradients.
So it may just be a toy problem that is there to introduce you in how to
Yeah, I mean,
integrate your quantum and your machine learning in the
Ye-
Qiskit thing.
yeah, and everything is worth going through, like as far as exercises, because even if I don't even think there was data set in this specific one. Even if you have a small data set like that, decrease in time or increase in accuracy can relate to, when we get more qubits and these types of things where it's significantly faster. Or if you're running you should be able to run multi-node, I think, for Qiskit and NVIDIA. But basically with a lot of these things, it's just it takes time to say, like, if you want to run a simulator that's 8 cores and corresponding to 8 threads, that can be tricky. And then if you want to do, a perfectly optimized multi-node GPU experiment, so, if you can't do it through Qiskit, you can with at least one other platform too. Any other questions? So there's a lot to learn. And a lot of times you're looking for things in quantum, but you'll learn so much more than you were anticipating, but you could use it for later. So you're hoping, as far as being an effective, machine learner, with Qiskit, eventually, basically, that it'll catch up in a good way. And so feel free. So if you have any questions, you can raise a hand. I see other things in the chat here. Did you the initial? Okay. And basically, it's a journey for sure. You learn by just, developing new stuff, based on other code, this type of stuff. It's meant to be like a building process, I would say. Anybody that we haven't heard from? So Saba or Han? And I did ask the question in the Qiskit Slack channel if there's more of these coming, and they said yes, but it's going to take some time. Most of these are considered quantum inspired. Like you just can't use quantum computers and machine learning workflows because of the noise, and you can't get the answers right away. It's just, or differentiation methods. I think you're strictly limited to parameter shift rule. Those types of like limiting things in hardware. And, these are just 12. So I would say Qiskit, their Slack channel has the most as far as the number of topics. Now, if you create one, I think it remains private. I tried doing one for QML. But the rest of the ones, the public ones, every single day you go on and there's new stuff. And the breadth of it it's pretty awesome. So anybody else new? So Timothy or Abe? Then let's see who else. So Risky or Javier? So Mobina, you should be able to get onto Slack. I don't think there's anything preventing anybody getting onto Slack. I don't run Slack. So they have events. It's error correction, dynamic circuits, you name it, it's up there.
So asking about the Qiskit Slack channel?
Yeah, Qiskit Slack.
Yeah, you just go to their website and find the link, click on it.
Yeah, I mean, you should be able to like like a Qiskit Slack, Google or something like that. The most I've had problems is it wants you to have some app. So sometimes when you click on links, that's the case. There's another button. But anybody else is like fundamental questions about quantum? How you could get started? So I would say this is intermediate to advanced. Like you have to know circuits and gates. So gates are the little squares, and then circuits, either shows the little gates or it puts it into like real amplitudes or ZZ feature map like a block. So and just the worst thing to do is just not keep developing. A lot of times we're limited in certain things. So we work with what we have. So if I try to do these awesome things with like, optimizers and certain types of differentiation and those types of things, it's another study, but sometimes that's what it takes. So from a very fundamental level, the whole purpose of quantum machine learning is to train, a model in a similar way to classical, but you're using quantum algorithms. Okay. So today, and this is why I say this 2012 PQC model that we have, needs to be improved, is this is done through rotating the, qubit over the course of time. And, you have a specific data set. Now, just like machine learning, you get a specific out loss and accuracy in models. And depending on how well these qubits are turned at specific times, dictates how well the performance of the model is. So to make a comparison in classical, if we're up to billions and trillions of parameters, in quantum, we don't need that many, we're still at that level due to, RAM issues and lack of understanding of, how big data sets move through circuits. Those two things need to improve. So I do see other people from other meetups, which is a great thing to see. And it's not as complex as, if you focus in on quantum machine learning, it's not as complex as, what others may say. If you're solely focused on the circuit and the algorithm, then you say, okay, well, if I keep adding layers, I'm going to keep adding parameters, right? So for instance, I did this study with 1 layer up to 10, and my optimal for a good data set that had, a good number of training images and good number of testing images was 8 layers. So it's 4 qubits. So 8 times 4 is 32. 32 parameters, quantum parameters, was better than any of the other 9 that were tested. Now, the other 2 data sets that I use, one kind of maxed out right away. It's binary. It already was fine. Now, the other one, it didn't have enough images per class, so I wasn't able to get it. It showed trends like the other good data set, but the data set matters a lot, just like in classical too. And I would be interested too, if anybody has, this classical experience, to, like, how does this, or how could classical, this emerging classical that we have today, also be included with quantum? And kind of when's the breakthrough going to be with these new architectures of quantum models?
Are you talking about things like transformers and
Yeah, I mean, it
some of
could
the
be
more
transformers.
high-end classicals?
Yeah, I mean, go ahead.
I haven't seen anything in that area related to quantum. Doesn't mean it's not out there though.
Yeah, and I had experimented with it, but I wasn't able to fully incorporate the quantum circuit into it. And it seemed to be running okay. I just had, for 44 classes, I had an extra row and an extra column of digits, basically. But yeah, every single, and everybody knows that, or not everybody, but like most people know, if you're in quantum, if you have a classical algorithm, you can do it quantumly. It's not always as efficient to do it that way, but that's the other approach, is basically to use quantum algorithms, despite, slowdowns in simulators, that can assist a deep learning neural network in ways that the DL network can't do on its own. And I was actually on a call this morning at QEDC, and it was hardware, and and it's the same type of tone as it was like a year ago. With a lot of this, it's just like, not huge advancements, I would say. So that's my remark, is basically just focus on very small things that quantum mechanically you could do to help a classical deep learning neural network. And to me, that makes sense, right? It's practical. So. Anybody else we haven't heard from? So I know it's fun and exciting stuff, and I can talk about very simple things with quantum all the way up to more advanced than what was talked about today. So. And obviously this week I focused on Qiskit. I've run a lot with Qiskit. I just haven't been able to, like, well, I presented on a lot, but like this was kind of like catching up with it. It's good to be agnostic with libraries, especially at this stage. And CERT could announce something new too. PennyLane's well on its way with QML. And, I guess, potentially ticket too. But, at this stage, it's not cemented as far as who will mostly, definitely be using a specific library for quantum machine learning. And then, so feel free to raise your hand, and it's completely fine. If all of this is just like way over your head, just raise your hand, and then, I can further, and probably other people here too, just break it down for you. And I'd be interested. I think most of the people here are probably developers. I do attract the medical crowd too. But what you want to learn more as far as, being a developer, medical developer, these types of things. I could try to answer timeline, forecasting questions too. Go ahead.
I have one question.
Yeah, go ahead.
In fact, last year, I had experimented with hybrid quantum GAN. That was for competition with Quantum Ecosystems Technology Council of India, and in fact, we won special nomination prize for it. Nevertheless, the reason I'm mentioning that is because therein, what we done was using a sample data set of RDKit to create new molecules using QGAN, and being hybrid, it was quantum generator and classical discriminator. Having said that, do you see the potential of completely quantum QGANs really accelerating drug discovery? I know it's a very active area of research, but what are your thoughts on that?
Yeah, I mean, they're promising. Most of them, I see the generator is a quantum circuit, and then
Right.
I think, in this specific one, we touched on one. I think Penny Lane has two tutorials with that. It's always trying to find out like the quantum advantage. Like, are you going to get, better accuracy across the board? In this quantum inspired machine learning field, when you design an algorithm which you think has quantum advantage, a good thing to do is dequantize it so it's the very similar algorithm classically to quantum. It's really hard to do because there's not that many of them, but it does show that the quantum algorithm that you want to use, say for hardware and for speed ups, is certified. So, I mean, for GANs and things like these things too, everything is just about the same, because it's just like it's using the PQCs from, this original model, from 2012, and it just needs a serious overhaul, like all of these deep learning, developments to go into a better quantum circuit, even if it's a lot less parameters. Yeah, and you can, some of these optimizers, you can change the circuit over the course of the run, so the quantum algorithm is actually changing as you do more mini batches, epochs, those types of things. But I think you're going to get that. There's like at least 8 of these medical image analysis, like classification papers, and it's very apparent that, like just the way that we design circuits and Composer, or even more, advanced circuits in lab, Qiskit lab, is that there needs to be something else that's giving it some quantum benefit that isn't classical.
Oh, okay, fair enough. I would also, if you allow me to shift a little bit, I mean, that's fair enough from QGAN perspective. Recently, over the past year or so, QNLP and QNLG are also gaining a lot of traction. But there as well, we haven't really seen anything beyond toy problems, or even toy problems are still at a elementary stage. Again, I'm a complete believer of QNLP, but again, how do you see the timeline from national language perspective?
There's not, I don't think we're talking any, sufficient deep learning neural network replacements with quantum circuits anytime soon. But I do believe, as far as specific tasks that say like did this specific part, or say like prepping the data better than deep learning could do at that stage, I think that's more realistic. Now, I've seen quantum algorithms before, classical deep learning neural networks. I've seen them after, So there's a lot of different research going on, but these things of like a full quantum NLP and quantum GANs, these types of things where the computations are for both GAN networks or both quantum circuits. I don't think that's anytime soon, but I do see as far as using it for there's research that has shown like we can put two different data sets on an exact opposites of a qubit. There's a paper for that, a Seth Lloyd paper, Maria Scholl, quantum embeddings. And then even like Kristen Temme, so he does that as well. And but yeah, I don't see it's as far as like a full quantum network. I think it's more like a supplementary thing, like a practical thing, like put it here in front, put it here after, or use a torch layer here, that in specific, but the whole thing, I don't see anytime soon.
Yeah. Okay.
But yeah, I mean, the whole thing with, quantum inspired is they say GPU quantum simulators will outpace quantum hardware for some time. That's based on research, and, Tom's hardware supported that. Now, the bigger, more interesting studies like Brookhaven National Lab and NVIDIA, Penny Lane, all these, multi-node GPU quantum simulator experiments, those are exciting. I don't have those notebooks, but it'd be interesting to see how exactly they're thinking. And they said oceans-sized data sets, how exactly they're thinking they could get, quantum advantage based on, using quantum here, quantum there, that type of stuff. But I think there was a Wall Street Journal, I think 2 weeks ago, Sandbox AQ was in it. And CEO Jack Hidary said that, they're using GPU quantum simulators, right? So if you want practical things done, it's typically that method. And why not make it QML, right? So they might be using quantum machine learning with that too.
Oh, yes, definitely. Thank you. In fact, yeah, I explore quite a lot using Kernel. I should do that with NVIDIA too. Thank you so much.
Yeah, you're welcome. Awesome. Any other questions or comments? I appreciate everybody coming on. And this goes for future discussions too. There's a repository on GitHub that I put up. It's probably the largest medical QML repository in the world. I haven't found, I literally spend every day on this. So that has, PDFs, presentation. It's got a lot of code, a lot of notebooks, and the R&D, behind it too. But this is where I think things are going, and the practical approach with quantum inspired medical. If we can dequantize algorithms, we don't even need a quantum simulator, right? So it's just like, we thought of the algorithm with a quantum circuit and then converted it into classical. Now it's a classical algorithm, right? So you don't actually need, quantum simulators. Awesome.
Hey,
yeah, go ahead, Ron.
You mentioned Jack Hidary, CEO of Sandbox AQ or whatever. For anybody here who's just starting their quantum journey, out looking for books and stuff like that, Jack's book on quantum is excellent. I read it cover to cover. I don't recommend it as your first book. Make it your second book, because it is math heavy, but there's so much packed into there. It's pretty incredible. But find another book that's like an introduction to quantum computing, and then get his book to fill in all the math and all the gaps.
Yeah, I appreciate that. He also has a GitHub too, and I think it's for the book.
Yeah.
And I mean, it shouldn't be, if anybody knows the name of the book, you can put it in the chat there. So any other last questions or comments? I'll have the presentation up. This will be up. And like I said, on GitHub, there's, well, they have their own GitHub. Qiskit, the modified ones, are up too. And I've done other, similar types of breakdowns for other ML platforms too. Awesome. Well, this has been discussion 103, Thursday, October 5th, 2023 for all IBM Qiskit machine learning tutorials seminar. My name is Kevin Krawczyk. I'm the founder CEO of Chemical Q Device. Thanks everybody for coming, and don't be afraid in future episodes to ask basic questions. Have a good night and have a good rest of the week. Take care, everybody. Bye.